Thank you. Thank you again. All right, our next speaker is Dr. Shade, who will be talking about space and ground-based data management at the Canadian Astronomy Data Centre.
I'm sorry?
You have to kill this.
Somebody's doing it. Somebody's doing it. Will you start the presentation, somebody, or do I have to do
Oh,
that?
you can do it.
How do I do that? I'll
Get
just-
to that and click. There you go.
I'm brilliant. Brilliant.
Physics.
No, it's a
And then go to
some,
display. Oh, yeah,
what do you
okay.
call these? Personal computers.
Right.
PCs.
Well, thank you very much for inviting me here to speak. So what I'm going to talk about is essentially, well, it's what's going on in Canada, but really it's about what's going on in the collaborations that we have, because I think the most successful thing that we can claim is over the past 10, 15, and 30 years, we've developed great collaborations and great ways to work together across many countries and many facilities. That's really what this is about. This work is supported by the Canadian Space Agency, but it's not done at the Canadian Space Agency. It's done as a roughly 50-50 cost-sharing arrangement between the National Research Council of Canada, which employs me, and the Canadian Space Agency, which funds the work. So I wanted to see what this proposal was about without reading the entire thing, so I just made a word cloud, and, well, the obvious came out. It's about open space science data. So the Canadian Astronomy Data Centre, CADC, began 30 years ago strictly and solely as an HST data repository. It began before the launch of Hubble and has continued ever since. So what has changed in 30 years? What I'm talking about here is what has changed for CADC, for the Canadians, but also to a large degree what's changed for a lot of us. So open data has been here since the beginning for us for the past 30 years. It's always been quite open data for Hubble, but for many other missions, all of the missions. In fact, we will not handle data that's not open. We will not make investments in that. So it's always been open data. We started with Hubble Space Telescope data, and then we expanded to include other space missions and ground-based data as well. We began as a data center that worked largely alone, but quickly began to grow a collaborative network, which took many years to grow. But now I feel we live in we function in a very collaborative global network. And that's the real success, I think, that we have to claim. In whenever it was, around 92, CADC produced the first web GUI for an astronomy data center. And now we've evolved into having IVOA standards for global virtual observatory. The reason I equate these two is that the web is kind of the model which stimulated people to think about approaches that led to the International Virtual Observatory Alliance. For us, we went from small data to very large data, and that has a lot of implications for where we are today. We went from being a data archive where people drew data out, like withdrawing from the bank, to a big service ecosystem where we no longer less than 10% of our data is delivered to users. It's delivered now from the data collections into another component of the ecosystem, and I'll show you a little bit what I mean by that. And we went from siloed data. We went from a situation where we had silos. We had an HST archive. We had a CFHD archive. We had a Gemini archive. We had all these separate archives. And they all had separate software, separate interfaces. And this was an untenable thing, because as the whole virtual observatory idea is based on integration of resources, integration of services, and we've broken down those silos now, as ESAC has done, as many others have begun to do now. Very much stimulated by the International Virtual Observatory Alliance work. So we were created in 1986. We have 21 staff members, and just for a sense of the scale, we have about 1 billion files, 2.6 petabytes. It's important to note that we move around 1.5 petabytes of data around in a year. Most of it is within the ecosystem, but it still has to move over some kind of network. We do, for process, we have a cloud processing system that's available to users, and we run, in 2016, 3.6 million jobs, and so on and so on. 500 core years, it's not an awful lot, but it keeps a small cluster of 500 cores busy pretty much the entire year. So the Open Universe Initiative, I must say, is a very, very familiar vision. I mean, this is what we've been talking about since before the Virtual Observatory was formed in 2002. We had Virtual Observatory meetings in 2001, and for some years before that, this is the kind of vision that we imagined for a functional virtual observatory. So it's a very, very familiar vision. And of course, I'm talking about astronomy here, and astronomy is one part of space science, and there are other components. And there's education and outreach, and there are definitely segments of this that are perhaps less familiar. But the point is that we've done a great deal of foundational work over the past 15 years, and we're very glad to see this initiative. What we have to do is find a very productive way to work together. Now, a little bit about collaboration. As I said, we began with the Hubble Space Telescope Archive, and we did that in collaboration with NASA and ESA. And over the years, that grew into more and more substantial collaboration. It began just with having an operational way to exchange data, but then it grew into something which eventually became the Hubble Legacy Archive, which was a method to produce science-ready data, that is, transparent data. And we deal with a lot more transparent data now than we used to. I would say certainly the majority by volume of data in the Canadian Astronomy Data Center is transparent data. It's science-ready. It's advanced data products. It took us a number of years to really come to this point where we could sign an MOU to work together for advanced data products or transparent data. And this way of working together gave us a lot of guidance in how to develop a more substantial interoperability of the data centers, and that's what's important for IVOA. So somebody was referring to this before, and I'm sure you've seen this: the fact that the big payoff is the archival research papers that would not have been possible without good data management infrastructure. So those are the papers, and it's more than 50%. You know, it's a factor of 2.5 for Hubble that would not have been done. So you're talking about thousands and thousands and thousands of research papers on this graph alone that could not have been done without good data management. But I will say it's not just good data management. It's also availability of open software and things like that. There are other aspects to this, but you've got to have the foundation of sharing data or you don't have anything. So I mentioned integration of data resources. This is what we call advanced search, and it's not advanced search, it's the only search that there is now at, the only GUI search that there is at the Canadian Astronomy Data Center now. We took 115 instruments from from 21 different collections, from a number of different observatories, and we unified them by creating an underlying common archive observation model, and we transformed all of those 115 instruments into one model. And this gives you a foundational level of integration of data that upon which we could build all of our virtual observatory services. All of our services are built upon that. And the most important thing, this is one of the most important things we've ever done, because it provides value to scientists, but it also provides a model for the process of profound integration of data and resources, a common model. It provides a process that you can use to expand this to other astronomy missions and to other research domains. If you want a multi-disciplinary data model, this defines the process that you would use to get there. And it can be done. It can be done. It's challenging. It took us 5 years to do it, but it can be done. The other integration we've done is we've integrated space and ground-based data. And of course, we have to do this because scientists don't use just space data, and they don't use just ground-based data. They pull together whatever data they need for their particular science goals. And so we had to do that level of integration. So I've already told you about the common data models. The other thing I should say is CADC is very much VO inside. The whole architecture is based on IVOA standards. And this is where Canada delivers data to. And yes, we do have a few Canadian users, but they're less than 10%. But in our cloud processing ecosystem, they're much larger fraction, fortunately. So IVOA, the International Virtual Observatory Alliance, has been working for a long time, and this has been, it's not just the standards we produce, that's the fundamental product that we try and create, but it's also the level of regular interaction and collaboration that's grown out of that. It's been an incredibly productive environment in which to work for a data center like ours. So the last point really is that CADC, because of the data volumes, this is the driving factor. The data volumes were so big that the old model failed to work, and we had to move from being a data center that delivered data to an operator of an ecosystem of compute resources for data-intensive astronomy. So this is the old model. Essentially, data came in from an observatory. We had discovery mechanisms, but after that, it just went out and you took it home. The scientists took it home, stored it on their home stuff, and processed it on their home stuff. Well, as data gets large, that doesn't work anymore. It just fails to work. So we have a variety of services in this ecosystem that we offer to users. And this whole thing is built, it's a platform developed and operated for the past 6 years by CADC and by some university collaborators, but done on hardware that's provided by the national grid infrastructure. So it truly is cloud, and it truly is distributed. It uses virtualization and so on. It uses containers. It uses persistent VMs to run services and all sorts of things like that. So the old model looked like this. The new model is much more complex because you have the observatories on the left. Now we have multiple inputs of data. In fact, we have 115 different instruments into this ecosystem. Inside the ecosystem, there's storage, there's personal storage, archival storage, there's processing of various kinds. There's kind of a lot of support for visualization and things like that. So typically what people do is they come in and they move data around, but they don't take it home. They move it from one part of our cloud to another part of our cloud, do the processing, do the visualization, whatever they want to do, they do it on that cloud. And the reason I bring this diagram back again is clearly, just as we needed to develop a global way to share data and a global infrastructure to enable the sharing of those data, we need to develop an international infrastructure that shares these cloud ecosystems as well. And this is going to be very challenging, but the data sharing was challenging as well. But we have to do that because the science teams that we support are very, very much international in scope. So we don't have any choice. We have to develop a global ecosystem for data sharing that supports all these science teams. So out of all of these things, I would say that the open data was a necessity, but there was a lot of work to do, and it's the successful collaborations that we've built over the years. And over the past 15 years, particularly with and through IVOA, that really has made this work. So we have a foundation of knowledge, expertise, and operational systems that I think Open Universe can use as a very powerful partner in what they're trying to do. Thank you.
Thank you. Questions?
Yes, I'll speak without microphone. Two observations actually. One of them regards what you showed of the Hubble space data and how much impact there is in being able to revisit archival data. But also picking a bit on what Julian Osborne was saying about Swift, I mean, we also have to ask the question, when the data that is first produced arrives within an interface where it can automatically integrate to many other data, how many new research you can do just from the fact that you can easily and readily integrate the new data with the data that's already into archival, not only from multi-wavelength bands, and this is something that your example of the Canadian data center shows very well. So this is one thing. And the second thing is, I think a step forward that the Open Universe Initiative is maybe looking at is how to transform these data centers into research tools. So not only centers where data is stored and you can play with them, but which you can use as an online instrument for developing your research. For example, in the ASDC, there is this SED Builder database. And it's very interesting because there you can plot and you can see the data in a way which is interesting for the way we think and the way we decide which kinds of objects that we are going to study and how we are going to study them. So I think that a new thing of the Open Universe Initiative is also to give this new step into transforming the online databases into research tools, not only databases.
Well, I think what I would say is, the infrastructure, the cloud infrastructure I've provided here, it provides some tools, but it certainly provides a platform on which it's very easy, without any investment of money, $0, just your expertise. You can go into there, deploy a virtual machine, install any software you want, and anything that you can install will run there, zero cost to you, and there's your research tool. Anything you want to do, it's there. The infrastructure is there.
All right, thank you again, and we have to move on.